So we've talked about the bookends, we've talked about knowing where we are in the world, we've talked about knowing what the world looks like. Recall from Michael's presentation about dropping the package off about how important it is to get right on top of the target, how close you need to get. Leonardo has been working on something that we've been calling the precision lander, and I'll hand it over to Leonardo.
Ok, buenas tardes jóvenes, mi nombre es Leonardo Herrera, soy estudiante del Centro de Investigación CICESE y el nombre de mi presentación es Aterrizaje Preciso. Don't worry, just I'm kidding. The presentation is in English, and I want to give an apology before continuing for my accent. It is not my first language. I'm Leonardo Herrera, student from CICESE Research Center, and the name of my presentation is Precision Landing. Here we have the mission, and the part that corresponds to my research is the number 6, that consists in locating and approaching a specific point. It is a challenging task that demands precision landing, robustness during the flight, and also the challenge of approaching that specific point by an aggressive maneuver is added. Based in this situation, the objective is defined as precision landing over a package or over a specific point by performing an aggressive maneuver by the quadrotor, of course. And for accomplishing that objective, a controller that drives autonomously the quadrotor from one initial point to one final point is designed. This controller is also designed with the property of working in two different environments. The first one in the left is an environment free of disturbances, and the second one is an environment with disturbances that can be turbulence, wind, etc. It is a scheme that describes the strategy I used for accomplishing the part of the mission that corresponds to me. From left to right, I show a block named Trajectory Generator, which produces a reference trajectory that needs to be tracked by the quadrotor. The next block, Robust Tracking Controller, is a block that generates the angles required by the quadrotor in order to track in the reference trajectory. The Attitude Controller block generates thrust and torques that make consistent the angles required to tracking the trajectory. The picture of the quadrotor represents the dynamics of this system, and the H-infinity filter estimates information that is required by the good performance of the controller. The rest of the presentation consists mainly in explaining in more detail H block, and I'm going to start with the quadrotor picture. There's equations, are 6 equations of second order that represent the dynamics of this aircraft. 3 of them represent the translational dynamics. The other 3, the rotational dynamics. X, Y, and Z represents the position of the center of mass of the aircraft relative to an inertial frame. And psi, theta, and phi represent the angles of the aircraft relative to the same frame. Psi is the angle around the axis X axis around the Z axis. Theta is the angle around the X axis, and phi the angle around the Y axis. Also, this model has U and tau, where U denotes the thrust used for moving the aircraft in the Z axis, and the thrusts are those that move the aircraft along yaw, the angles yaw, pitch, and roll. Also, W represents the turbulence that is present during the flight, and Now we are in the next block that is highlighted in red, is the H infinity filter. This block provides information that is required for the good performance of the controller. It is based in measuring available information for estimating an unavailable. For example, the input of the filter is y start, represent the position of the aircraft measured by, for example, the beacon system that we have here, or can be the GPS also. And the output of the filter is given by heat that represents the position and velocities of the aircraft. Here, P and Q are two important factors for the well functionality of the filter that are obtained by solving the two algebraic Riccati equations. And once obtained this information, we are now in the block named Robust Tracking Controller. And here we can appreciate the factor heat, that is the estimation of the filter. The factor P gives robustness to this controller, and what the controller generates is the suitable quantities of pitch, roll, and thrust for moving the aircraft along a reference trajectory. Here we can appreciate also the control depends on some variables with subindex D, and which are the reference, which is information from the reference trajectory is given by xd, where x0 is the solution of the harmonic oscillator equation with these parameters, and xf is the destination point for the x variable. For the variable, the coordinate y is defined the reference trajectory in the same way, and the reference for c is given by the straight line equation with negative slope. Here we have the reference trajectory generated by these three equations, and here we have some numerical results. And this is the result which present the undisturbed situation where no perturbations are present. The reference trajectory is the red one, and the blue one is the quadrocopter trajectory. We can appreciate how this aircraft tracks the reference trajectory in order to get the destination points. The next results present the situation where disturbances are present, are described by these W's. Starting from one initial condition, the quadrotor, it tracks the reference trajectory in order to get the destination point, but in different as the last graphic, we can appreciate here that the deviations that the quadrotor has relative to the reference trajectory is due to the disturbances. And now conclusions. The controller designed here demonstrated numerically capability for autonomously driving the quadrotor from one initial altitude to the target, and also the solution of three differential equations were used for planning the reference trajectory of this aircraft. And an additional conclusion is that the tracking of this path has been robust under uncertainties, and numerical results have been shown for corroborating the proposed control scheme. Gaining experience is too much experience, and first a better comprehension of the dynamics of this system, and I learned also that there are physical restrictions like limitation in motors, the floor is another physical restriction that exists, relation between thrust and torque with motors. Usually we design thrust and torque, but we are not concerned about the relation between them and the motors. The data distribution service system, the joystick for sending commands to the aircraft, the sensor icon system, the operating system Linux, and Git. Accomplishments, we designed the trajectory generator, the filter for estimating unavailable variables, and the robust tracking controller design. Thanks to all the Autonomy Incubator team, especially to Paul Rotter, who is not here, but I'm so grateful with him for bringing here to this unforgettable experience, to John Copper for being so patient with me during the stay, and to Ana Trujillo for helping me with my presentation, and to Jada, Christy, and Carly, in general to NASA, user A, and thanks to Mama Bear also. That's it from my own case, and thank you.
Leonardo, I have one question. What was the most difficult thing you had to, you were challenged with this semester? It can be technical or not.
There were many things, all related with practical stuff. It was my first practical experience ever. I have been working with theoretical results, mathematical development, and here I learned too many practical aspects, how to implementing the controllers in the digital computers, and it was a really was a valuable experience for my life, for my academic formation, and also the English was another additional challenge for me. But everything was amazing. I'm really glad and grateful with all the people who was around me helping.
Great. What you said, the very first answer that you gave is a very important one to remember. Applied robotics, non-academic, kind of studying the smaller systems, but integrating these systems of applied robotics is incredibly difficult. It's a very hard problem. Mm-hmm. And going from an academic setting to a practical or usage setting, it's a different field, a different world. And all you can do as many simulations as you want. You can prove as many theorems as you want until you actually go out and fly it in the weather, in this non-deterministic type of environment that we live in, non-linear environment. That's the real proof, and it's very difficult. But thank you. That's a very, very good answer.
Thank you.
And doing it 10,000 times in a row.
Yeah. YouTube live.
YouTube live. All right. Well, Leonardo, thank you. One more.